Hello students, welcome back, and today we are going to discuss the last phase of application of the concepts of chemical potential in real systems, and we are at the end of our discussion on electrochemical equilibrium. So, let us see the kind of applications that we have already looked at. We have already seen the determination of standard molar entropy and enthalpy change associated with a cell reaction. We have talked about how to determine activity coefficients of an electrolyte and find out solubility product of a sparingly soluble salt. So, today we are going to talk about determination of the standard reduction potential of an electrode, and then also have a look at how to determine pH of a solution. As I understand that we have already discussed the principles of doing so in my lectures. So, today we are going to look at some of the numerical examples of these two processes of determination. So, let us have a look at the problem 1. So, here we are going to find out the standard reduction potential of the silver chloride electrode. And for this purpose, we are going to use this particular cell where I have coupled the silver chloride half electrode with a standard hydrogen electrode. So, how do I know it is a standard hydrogen electrode? Because I am maintaining the hydrogen gas at 1 bar, and here instead of maintaining the HCl solution at unit activity, I am using an aqueous solution having a molality of M. Now, going ahead, I am going to use some measured cell potential which have been obtained by varying the molar concentration of HCl in the cell. So, as you see that I have changed the molality from 0.322 into 10 to the power of minus 2, and I have gone up to this number. Correspondingly, the cell potential varied from 520.5 millivolt to 449.7 millivolt. So, the task is looking at this data, can I find out the standard reduction potential of the silver chloride electrode, which has been used as the cathode in my electrochemical cell. So, let us go ahead and try and see how we solve this problem. So, obviously, the standard procedure would be I shall start by writing down the half cell reactions. So, here I find that the reduction reaction for the cathode on the right, that is silver chloride solid, it takes up electron, gives rise to silver solid and releases chloride ion in the aqueous medium. And the electrode potential, the standard electrode potential for this electrode, silver chloride electrode is ER naught C. Now, I can also have this reaction H plus aqueous being reduced to half of hydrogen gas, that is half mole of hydrogen gas with the standard reduction potential of 0 volt. And I am going to use this reaction in the oxidation form at the anode, which has been put on the left. Therefore, what I will do is I will subtract the second equation from the first equation, and then I will write down the net cell reaction as silver chloride solid being reduced to silver solid and half mole of hydrogen gas being oxidized to 1 mole of H plus in the aqueous medium, and in this process 1 mole of Cl minus aqueous is also released in the aqueous solution. Now, what are the different informations that I learn from here? Obviously, the first information that I get is the E naught cell, the standard cell potential, that must be equal to the standard reduction potential of the silver chloride electrode. And then the other information that I have is for the net cell reaction, I am using the n equal to 1, that is the number of electrons transferred is equal to 1. Now, going ahead then with this information, I will write down the Nernst equation for the cell potential. When I do that, so I start by writing E cell, that is equal to E naught cell, then minus R T by N F, then the logarithm of the ratio of activities of products with the activities of the reactants. We have seen this before, and we also know that what happens by standard convention is I can put the activities of this pure solid and the hydrogen gas at 1 bar as equal to 1. So, correspondingly at 298 K, by using the values of R T by N F, I can very easily write down that E naught cell is equal to minus 0.0591 log to the base 10, then activity of H plus aqueous into activity of Cl minus aqueous. Now, you must realize that whenever I am writing down this equation like this, I am actually using the E naught cell in volts and E cell also in volts, because I have used this number, the number that you see here, this is in volts. So, going ahead, I can write down that the cell potential in volts, that is equal to the standard cell potential in volt minus this number into log to the base 10 of activity of HCl aqueous. So, now I have reached a point when I can start putting in information from the cell that I have used to move ahead. So, that is what I will do. I understand that for the HCl solution, which is a univalent electrolyte, the activity of the aqueous HCl solution is m square gamma plus minus square. As we have seen, m is the molar concentration of HCl in the aqueous medium, and gamma plus minus is the mean activity coefficient of the electrolyte in water. So, if I put this back over here, this is what I get as my working formula for the given electrochemical cell. Now, then what I will do is I will just separate out the terms from whatever I have within the log and take the m dependent term to the left hand side. So, what do I now have on the left hand side? E cell plus 2 times this number, which is 0.1182 log to the base 10 m, that is equal to the standard reduction potential of the cell, which is essentially the standard reduction potential of the silver chloride electrode, minus the term which now depends on the mean activity coefficient of the electrolyte. Now, at this point I must remind you, although I am talking about the silver chloride electrode in the colloquial way, if I am talking about the standard reduction potential, actually I should be writing silver chloride silver electrode. So, this is implied as you see over here. Now, coming back to the highlighted formula, I am now going to use the following. I am going to find E naught cell using this formula, and here I am going to point out that whatever I have on the left hand side of this equation involve known values of both E cell and m. Therefore, I know the left hand side of this equation completely. But what do I have on the right hand side? Right hand side, I have two unknowns. First, the standard reduction potential, which I am going to find out, but then again I have another unknown quantity, which is the mean activity coefficient of HCl in aqueous solution. Therefore, to be able to find out E naught cell, I must know how to evaluate gamma plus minus. And obviously, you understand that then my working formula is going to be simplified in this way, that let me say E prime is E cell plus this number into log to the base 10 m. That gives me E prime equal to E naught cell minus 0.1182 log to the base 10 gamma plus minus. Therefore, if I know gamma plus minus, then I can use it to compute the corresponding value of E prime and obtain E naught cell. Okay. So, that is the basic idea over here. Now, going ahead, obviously, one of the ways in which you can determine gamma plus minus of the aqueous solution is by using the Debye-Huckel limiting law. So, let me remind you what the Debye-Huckel limiting law is all about. It says log to the base 10 gamma plus minus, that is equal to minus 0.509 multiplied by modulus of the stoichiometric coefficient in the formula of the number of positive ions present in the formula of the electrolyte multiplied by the number associated with the formula of the negative ion in the electrolyte. So, in the case of HCl, nu plus is equal to 1 and nu minus is also equal to 1. I will take a modulus of this product multiplied by root over of I, where I is the ionic strength whose definition we have seen before. Okay. So, for HCl, I can very easily write down that I is equal to m, that where m is the molality of the aqueous solution of HCl. So, this means that I can very easily write down log to the base 10 of gamma plus minus, that is proportional to root m. But please remember, whatever I am writing out over here, that is valid at 298 Kelvin. And I have given you the experimental data at 298 Kelvin, and therefore, now I can go ahead and rewrite the E prime value as E naught cell, then plus 0.1182 into 0.509 into root m. Okay. So, that gives me E prime, that is equal to the standard reduction potential of the cell plus this number multiplied by root m. Now, look at this particular expression very closely. So, this is going to be my working formula to find out E naught cell. But if you would remember that I have a set of values of m with respect to and the corresponding values of E for each value of the molality of the solution used. And my working formula says that I know E prime under the given experimental condition, because E prime is nothing but E cell which is measured into plus 0.1182 log to the base 10 m. Therefore, I know E prime from the experimental data, and I see that I also know root m at each experimental data. As a result, I can plot E prime as a function of root m. So, you can either carry out this plotting in a graph paper, or you can use the method of least square fitting, and then you can show that the slope of the straight line in this particular case the intercept is equal to 0.0602 and the intercept is going to be E naught cell. And we already know that E naught cell is nothing but the standard reduction potential of the silver chloride silver electrode, and therefore, from the intercept you should be able to show that the standard reduction potential that I was aiming to obtain is nothing but 0.223 volt. So, that winds up our discussion of the first problem, where I have used the measured cell potential as a function of different molalities of the aqueous HCl solution to find out the standard reduction potential of a half electrode by coupling it to a suitable standard electrode. So, let us have a look at a second problem, where instead of using the hazardous gas electrode, we are using two well known standard electrodes. The first of all, one is known as the calomel electrode, and the second one is known as the quinhydrone electrode. And these two electrodes are dipped in an acid solution of activity A, and this acid solution is having the formula HA. And when you use this electrochemical cell, you can measure the cell potential at 298 Kelvin, and it has been found to be 190 millivolt. So, now our task is to find out the pH of the acid solution. So, let me assume that the acid solution is dilute enough, so that later on, as I will make an approximation, its activity will be replaced by its concentration. As you understand that this is not necessarily required, but I will come back to this point later. So, first let us try and see if I need any other data to solve this problem. Obviously, I have to look up the standard data table and find that the standard reduction potentials of the two electrodes are as follows. It is 0.2442 volt for the calomel electrode and 0.699 volt for the quinhydrone electrode. So, obviously, we will once again start with our usual exercise of writing down the cell reaction, but just to give you some idea about what these electrodes are, let me first have a look at the calomel electrode. So, a calomel electrode is prepared by having a glass compartment of this shape, in which a tube has been inserted. In this tube, the one end of the tube is sealed by a glass disc, and here you have put in two different materials, okay? And this is a platinum wire. So, let me point out the different components of the electrode. So, you have a platinum wire which is dipped in liquid mercury, which is present here, and this is in contact with a paste of liquid mercury, mercurous chloride solid and potassium chloride solid. And this entire tube is immersed in an aqueous saturated solution of potassium chloride. And here you see that we have a point which can be dipped in the acid solution to create the electrical contact. So, in this case, as you understand that the calomel electrodes, although they are quite well characterized, this is also a bit hazardous to handle because of the use of liquid mercury and the mercurous chloride paste over here, because these are hazardous materials. Okay. But this calomel electrode gives you a very stable standard reduction potential, and therefore, it has been widely used in the literature, and that is the reason why we have chosen to use here in our numerical exercise a calomel electrode as the anode. Now, if you look at the half cell reaction in the reduction mode, what you see is mercurous chloride on taking up electron gets converted to mercury liquid and releases in the solution to chloride anion. Okay. And here, as given by the data, I find that the standard reduction potential of the calomel electrode is plus 0.2442 volt. Now, moving ahead, if I look at the quinhydrone electrode, the quinhydrone electrode is a complex of Q and hydroquinone, that is quinone Q and hydroquinone, which is given this notation QH2. Okay? And these are having well defined chemical formula which you can look up. But what happens here to us, we are interested in the Hufsel reaction, where we find that aqueous solution of quinone in acidic medium gets reduced to form QH2 in the aqueous medium. Okay? And the standard reduction potential of this electrode is given by plus 0.699 volt. Okay? So, going back then, I can compile the Hufsel reactions like this by writing down reduction at cathode. So, this is the Hufsel reaction corresponding to E naught R that is equal to plus 0.699 volt, and then I have the Hufsel reaction for the calomel electrode, for which I will have oxidation at anode on the left, and therefore, the net cell reaction turns out to be Q aqueous being converted to QH2, that is the hydroquinone aqueous in the acidic medium. So, and we also have mercury liquid being converted to mercurous chloride solid. Okay. So, what are the essential informations I note by doing this exercise? First of all, I find that the standard reduction potential of the cell now is given by E naught R minus E naught L, and therefore, E naught cell is equal to 0.4548 volt. And I also note that for the way I have written down this net cell reaction, the number of electrons involved in the electrochemical cell reaction, N is equal to 2. So, now I will go ahead and write down the cell potential from Nernst equation. So, when I do that, I write that E cell is equal to E naught cell minus RT by NF, then logarithm of whatever activity I have of the products divided by the activities of the reactants, each raised to the power of the stoichiometric coefficient of that species in the balanced net cell reaction. Okay. So, obviously, this is going to be the ratio that I am going to take a logarithm of. Okay. Now, once more what I will do is I will use the conditions such that I have a standard condition for the quinhydrone electrode as well as for the calomel electrode, so that my cell potential now simplifies to this equation. And therefore, from the Nernst equation I will say that the cell potential is dependent on the standard cell potential plus RT by F logarithm of activity of HCl. Okay, so, moving ahead. Now, from this equation we further note that activity of HCl is activity of H plus into activity of Cl minus, and in HCl, in this univalent electrolyte, I can replace this activity by square of the activity of H plus ion. So, accordingly what I will do is I will go ahead and put this information over here. Now, this gives me the chance to make an approximation that E cell will now be approximated by E naught cell plus this number into log to the base concentration of log to the base 10 concentration of H plus ion. So, as I said, in this particular problem, I am going to make this approximation that activity of H plus can be replaced by activity or the concentration of H plus, because by definition I know that pH is minus of log to the base 10 concentration of H plus. So, going ahead, what I find is E cell now is given by E naught cell minus this number multiplied by pH. So, what I will do is I will take this equation, rearrange it, put the value of RT by F at 298 Kelvin and find out the pH of the solution. And the answer is pH of the solution that gives you 190 millivolt at 298 Kelvin using this cell has a pH equal to 2.24. So, these are the two problems that I wanted to show to you, so that you understand how to use electrochemical cells to find out quantities which are useful in many other applications. Thank you.